And hello and welcome back. In the last video, we looked at the concepts of voltage, current, and resistance. And we said voltage is something that pushes a current through a circuit, through a conductor. Voltage is measured in units, called volts. We said current is a flow of charge or charged particles, and usually, but not exclusively, these charged particles will be electrons. And we said current is measured in units known as amps. Resistance, for its part, is something that limits or reduces the flow of current in a circuit, and resistance is measured in units known as ohms. It's important to know the measuring instruments for each of these quantities. Voltage is measured in using an instrument known as a voltmeter, that's its symbol. Current is measured with an ammeter, that's its symbol. And resistance is measured with an ohmmeter, there's the symbol for an ohmmeter. However, in practice, all these functions are usually contained in an instrument known as a multimeter. So in practice, a multimeter will carry out all these functions. But in an exam or when you're describing an experiment, it's very important to actually use these symbols so that it's very clear what quantity you are actually measuring. Now, we looked at the relationship between voltage, current, and resistance, and we said this relationship is commonly known as Ohm's law. And we defined Ohm's law saying that Ohm's law states that a voltage is directly proportional to the current if the temperature of the conductor remains constant. And you can also describe Ohm's law in an expression that is labeled voltage is directly proportional to current. So in an exam, if you were asked state Ohm's law, put it in words like that. That would be absolutely fantastic. That is a definition and should always be remembered. Or if you're asked for an expression of Ohm's law, voltage directly proportional to current, labeled like that, is perfectly acceptable, or better still, do both. One little note on the relationship between temperature and resistance for a metallic conductor. And when, of course, I talk about a metallic conductor, I mean a piece of wire, piece of copper wire. Well, when the temperature of a metallic conductor, such as a wire, increases, its resistance increases as well. This graph here illustrates that point. As the temperature of the metallic conductor increases, its resistance in ohms increases as well. And this is very important to note because this is why Ohm's law only holds for a conductor if the temperature of that conductor, if the temperature of the wire remains constant. That's a point we'll be coming back on again, so bear it in mind. Now, it's very important to remember that some conductors obey Ohm's law and some conductors will not obey Ohm's law. For some conductors, voltage will be directly proportional to current. For other classes of conductors, it will not hold. So, things like resistors and things like metallic conductors, which are normally going to call just coils of wire, these will obey Ohm's law. So in simple terms, if you double the voltage between the ends of a resistor, the current flowing through it will double. If you triple the voltage between the ends of a resistor, the current will triple, because for a resistor, voltage is directly proportional to current. Similarly, for a metallic conductor, and that's what the syllabus states, metallic conductor, when they mean coils of wire, then if you make the voltage between the ends of the coil of wire 5 times bigger, the current will become 5 times bigger, because voltage is directly proportional to current for a metallic conductor, with of course the caveat that the temperature does not increase or the temperature does not change. So resistors and metallic conductors, these obey Ohm's law. But some devices that do not obey Ohm's law would be, examples of them would be semiconductor diodes and filament bulbs. A filament bulb, of course, is just a bulb enclosed in a glass case with a gas inside, usually nitrogen, and a wire or a filament or a metallic conductor that actually literally, when the current passes through it, it gets red hot and then white hot and gives out light. So a semiconductor diode will not obey Ohm's law. In other words, if you double the voltage between its ends, you will not double the current. If you triple the voltage between its ends, you will not triple the current. Voltage and current are not directly proportional for a semiconductor diode. Similarly for a filament bulb, whatever you do to the voltage, the same ratio will not happen to the current. So if you double the voltage between the ends of a filament bulb, you will not double the current, because voltage and current are not directly proportional for a filament bulb. Filament bulbs, semiconductor diodes, do not obey Ohm's law. And I want you to think about this for a minute. Why do you think a filament bulb does not obey Ohm's law? Well, think of what we've said about Ohm's law earlier. Pause on this and think about it for a couple of seconds. So can you work out why a filament bulb will not obey Ohm's law? Well, if you related this to the temperature of the bulb and its resistance changing, you have done very well. Because for a filament bulb, and when we say filament, we mean the little metallic conductor or wire inside the bulb that literally gives off the heat and gives out light as a consequence, then filament bulbs do not obey Ohm's law, because when the temperature of the filament increases, its resistance will also increase. That is the graph there that illustrates that point. As temperature of a wire goes up, its resistance also goes up. And that is why a filament bulb will not obey Ohm's law, because its resistance changes as its temperature changes. And I think we all know that these filament bulbs get very, very hot. Their temperature gets increases quite a lot when you use them, and that changes its resistance. For that reason, they do not obey Ohm's law. It is very important to remember that when a component like a resistor or a metallic conductor does obey Ohm's law, that if you measure the voltage between its ends and change it, and measure the corresponding current passing through it, and plot those points on a graph, then the graph will be a straight line through the origin. And that tells you at a glance a graph of voltage in volts against current in amps that is a straight line graph through the origin. Then you can immediately say that voltage is directly proportional to current because it is a straight line through the origin, and this means that Ohm's law is obeyed. If you then pick 2 points on the graph and find their mathematical slope using the slope formula, the slope of that will be the resistance of the resistor. We know this because voltage divided by current is the definition of resistance. And when you get the slope of the graph, you're really dividing voltage by current, and you will get the slope as resistance of the resistor. Using Ohm's law, voltage equals resistance by current, or voltage is directly proportional to current, we can juggle these terms around and find the formula resistance equals voltage divided by current. Now, even though we said earlier that resistance is something that reduces or limits current in a circuit, and the bigger the resistance, the more it reduces the current. So a high resistor will only allow a low current through it, and a small resistor, a low value resistor, will allow high current through it. But that's just an idea of resistance. Here is the actual definition of resistance. Resistance equals voltage divided by current. That's a very important definition, so I should be highlighting it. If you're ever asked what is resistance or define resistance, you would say resistance is the ratio of voltage divided by current, and you would also give that expression, that formula, but you will label each part. That is very, very important. The unit of resistance is the ohm, and that's the symbol for ohm, the Greek letter omega. Now we have defined resistance as resistance equals voltage divided by current. And as they say on the t-shirt, resistance is not futile, it's voltage divided by current. But now we want to do one more thing. We want to define the unit of resistance, the ohm. What does it mean when we talk about 1 ohm of resistance? Well, we're going to use the definition of resistance. Resistance equals voltage divided by current to define the ohm, the unit of resistance. So if we take a resistor, and between the ends of the resistor we apply a voltage of 1 volt. So we connect 1 volt between the ends of the resistor. Well, a voltage, by definition, will push a current. So a current will flow through this resistor. And let's just say, for our purposes, that the current flowing through the resistor is 1 amp. So a voltage of 1 volt will drive a current of 1 amp through our resistor. The question I'm going to ask you now is, what is the value of the resistance of the resistor? How many ohms is it? Well, remember our definition. Our definition of resistance is voltage divided by current. So we're going to use that. So what is the resistance of this resistor? Well, if you said in your head that resistance equals voltage divided by current, so the resistance of the resistor is 1 volt divided by 1 amp, 1 over 1 is 1, and in honor of George Simon Ohm, who came up with Ohm's law, we honor him with giving him the unit of resistance. Then the resistance of that resistor by definition is 1 ohm. So we use this ID to define what we mean by 1 ohm. 1 ohm is the resistance of a resistor if a voltage of 1 volt between its ends pushes a current of 1 amp through it. So 1 ohm is the resistance if a voltage of 1 volt causes a current of 1 amp to flow. That is a definition, and that is something you should learn. In future videos, we will continue on, mainly on the experiments, and there's 8 excellent experiments in this, and we hope that we will be doing some of them live when we get back to reality. One more thing, next time we meet, I just want to talk about the actual subtle difference between what we call direction of current flow and direction of electron flow. That's something that has annoyed a lot of students over the year. We'll leave that till next time. Thank you for listening. Take care.